In this video, we're going to look at stretching a sine wave out. We're looking at just stretching it out. Now, on the board I have some preparation done. I've got Waggle's sine of x, what I call a standard table. And I also have, this is what I call a standard graph for the sine function. When I don't have any shrinking or stretching going on, I generally let one tick mark on the x-axis be pi over 4 units, 2 tick marks on the y-axis be 1 unit. And to me, this is a standard sine wave graph. We're showing at least 2 periods from 0 to 2 pi. This will be 2 pi. And from negative 2 pi to 0 is another period. Now, what I want to talk about is the graph of x over 2, or the sine of x over 2. Now, just like in the last video, we saw that the sine of 4x made the sine wave go 4 times as fast. We saw a horizontal shrink. It compressed it. It's kind of like an accordion, okay? With 4, bigger than 1, you compress it. If you're smaller than 1, like x over 2 or 1/2 x, then you're going to stretch it out, okay? In other words, it's going to take this guy twice as long to get to a normal period. Now, same table set up as before. The top line is x, the values of x that we're going to plot. X over 2, the argument of your sine function, and then the sine function itself, sine of x over 2. Now, I want x over 2, the argument, to be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Because those are special values for sine. That gives me 0, 1, 0, negative 1, and 0. The trick here is to find out what values of x correspond to those special values for the x over 2, the argument. And it all comes out of this little equation right here. X over 2 equals pi over 2. You want this argument, x over 2, to be equal to pi over 2. So what value does x have to be? Well, if you solve this equation for x, you multiply both sides by 2, you'll see that x has to equal pi. If you think about it, solving this equation, x equal one of these numbers, you're just going to multiply all these numbers by 2. So pi over 2 becomes pi, by the way, 0 and 0. This pi becomes 2 pi. This becomes 3 pi, and this becomes 4 pi, because 2 pi times 2 is 4 pi. All right, now let's plot these points. Now, I'm going to be able to get probably just one period on this graph with the limitations of the chalkboard and with the scale that I've set up. Normally, what I do is I let the distance on the x-axis, one tick on the x-axis, be about half the distance from here to here. Okay? So normally I would let this be from, one tick mark would be from 0 to pi, half of that is pi over 2. We got pi over 4, okay? So we still have the point 0, 0, but now to get x has to get all the way to pi before the sine reaches 1. So pi puts me here. On this 4 pi over 4 is pi. There's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Then I have to get to 2 pi before I'm back at 0. And if you look at it, I got 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4 puts me down at negative 1. So that's not even a whole period. Now if I come over here, 1, 2, 3, 4 puts me down at negative 1. 1, 2, 3, 4 puts me back at 0. And then 1, 2, 3, 4 puts me up at 1. So what you have here is a long, stretched out sine wave. It looks something like that. Okay? All right, so when this number is smaller than 1, think of the sine or the cosine or any of the trigonometric functions as kind of like accordions, sine and cosine especially. When that number is smaller than 1, you're going to see a horizontal stretch. It's going to take it longer to get through a whole period. When this number is bigger than 1, you squeeze your recording down. It's going to get there quicker. Okay? All right, so in the next video, we're going to look at phase shifts, and we're also going to look at shrinking and stretching the amplitude. All right, thank you.